All right, let's talk about a huge misconception in machine learning. This obsession with 99% accuracy. We're always told that a super high accuracy score is the holy grail, right? But what if I told you that's actually a trap? Let's get into why.
So let's just start with a really simple question. Imagine you've built a model and boom, it's 99.9% accurate. That's amazing, isn't it? Pop the champagne? Well, hold on, because in some of the most important situations, that beautiful number is actually hiding a complete and total failure.
And to see exactly why, let's imagine a scenario. Let's say we're building a model to detect a really rare but very serious disease. And this disease only affects, say, one person in every 10,000. Our job is to screen the entire population and find that one person.
Okay, now picture a model that is, let's just say, super lazy. All it does for every single person is predict no disease. That's it. So out of 10,000 people, it's going to be right 9,999 times. That gives it an accuracy of 99.99%. But it completely misses the one person who's actually sick. So despite this almost perfect score, the model is 100% useless. It doesn't help anyone. This is the accuracy trap.
All right, so if accuracy by itself can be so misleading, what are we supposed to look at? Well, we need to dig a little deeper. We have to break down the model's predictions into 4 different outcomes. And to make this super clear, let's switch gears to an example we all deal with every day, a spam filter.
First up, we've got the true positive. This is the good stuff, the hero moment. Your model sees a spam email. It correctly says, yep, that's spam. And shoop, sends it right to your junk folder. Perfect, exactly what we want it to do.
Next, we have the false positive. Now, this is when your model gets a bit overzealous. It sees a really important email, like a job offer or a note from your bank, and it mistakenly throws it in the spam folder. This is super annoying, and it could be a really costly mistake. The third one is the true negative. This is the silent workhorse of your spam filter. It sees a normal, legitimate email and just lets it pass right through to your inbox, as it should. This is happening constantly, hundreds of times a day, and you never even think about it.
And finally, there's the false negative. This is when the spam filter messes up in the other direction. A piece of junk mail slips through the cracks and lands right in your inbox. It's an annoyance, for sure, but usually not as big of a deal as losing an important email. So we can take all 4 of these outcomes and organize them into this really simple grid. It's called a confusion matrix. And it sounds complicated, but it's not. It just gives us a crystal clear picture of how our model is performing, showing us what it predicted versus what was actually true.
Now, to really make sense of this matrix, we need to bring in 2 expert detectives. Their names are Precision and Recall, and they help us ask much smarter questions than just, hey, how accurate is it? So our first detective, Precision, is all about quality control. It asks a really specific question. Of all the times we pointed a finger and yelled spam, how often were we actually right? It's a measure of purity. If you have high precision, it means that when your model says something is spam, you can be pretty darn sure it's right. Our second detective, Recall, is focused on something different, coverage. It asks, of all the spam emails that were actually out there, how many did we manage to catch? So Recall is all about being comprehensive. High recall means you're doing a great job of finding most of the actual spam. And putting them side by side like this makes the difference pop. See, Precision asks, when I flagged something, was I correct? But Recall asks a totally different question. Out of everything I should have flagged, how much did I actually find? They're just 2 fundamentally different ways of judging performance. Okay, but here's the inevitable catch. This is the tricky part. In a perfect world, we'd have 100% precision and 100% recall. But in the real world, they're almost always fighting each other. Pushing one up often means pulling the other one down. So why does that happen? Well, it's because most models don't just give a simple yes or no. They give a confidence score. They might say, I'm 85% sure this is spam, and we get to decide the cutoff, the threshold. We could say, okay, anything over 80% confident, we'll call it spam. And we can slide that threshold up or down. And that's where this whole trade-off comes into play. Let's see how this plays out. Imagine we set a really high threshold. We tell the model, don't you dare flag anything unless you are 99% sure it's spam. What happens? Well, our precision will be fantastic, right? We'll have very few false positives. But we're going to miss a whole bunch of the less obvious spam, so our recall will be low.
Now, what if we do the opposite? We set a really low threshold, maybe just 50% confidence. Now we're casting a super wide net. We're going to catch almost every single piece of spam out there, which means we'll have amazing recall. The downside, we're also going to accidentally flag a ton of perfectly good emails, which means our precision's going to be awful. So, if we can't have the best of both worlds, how on earth do we choose? Do we go for high precision or high recall? Well, the answer, and this is the key, depends entirely on the specific problem you're trying to solve. This is where you have to ask the most important question. What is the cost of being wrong? Let's take our two examples. With a spam filter, a false positive, losing a critical email, is a way bigger deal than a false negative, just seeing one more annoying spam message. So for spam, you absolutely prioritize precision. But now think about our medical screening example. A false negative, telling a sick person they're healthy, is a disaster. It's way, way better to have some false positives, where healthy people just have to get a second test, than to miss even one actual case. So there, you have to prioritize recall.
And that really is the heart of it all. The most accurate model isn't always the best one. Not even close. The best model is the one that's designed to minimize the most costly type of error for whatever you're doing.
So I'll leave you with one last thing to think about. Picture a self-driving car and its system for detecting pedestrians. What's the more costly error here? Is it a false positive, where the car slams on the brakes for a shadow on the road? Or is it a false negative, where it fails to see a person stepping out in front of it? You see, this choice between precision and recall isn't just some abstract technical decision. Sometimes it can literally be a matter of life and death. Thanks for joining me.